Hello everyone, welcome to Professor Cloud. Today we are going to talk about EKS IP exhaustion problem. IP exhaustion is a common problem in EKS. We have seen many teams and organizations struggling with this issue. In this video, we will be discussing the EKS IP address exhaustion issue and how to solve it. We will be referring to custom networking in order to do so, and we will also provide a live demo for your convenience. We have divided the video into different sections. Problem, why this happens, solution, demo. Ideally, when your manager or leader asks you to create an EKS cluster, you use an existing VPC or sometimes you create a fresh VPC and start consuming it. You create your EKS cluster and start using it without knowing of this problem. Since you have used an existing one which is shared with other workloads in your project, or you might have created a new VPC, but the subnet range is not having enough IPs to allocate to each workload. As the time goes and the workload starts to increase, we see that there are not enough IPs in your network. And then a time comes when there are no IP present to allocate to any new pods, and all your pods will be in pending state. And that's called as IP exhaustion problem. To understand why this happens, we might have to start from AWS EKS networking. AWS EKS uses KTS CNI plugin to support the networking. What is this CNI plugin? AWS CNI plugin is used for pod networking in Kubernetes, which uses ENI, which called as Elastic Network Interface. To understand the problem, let's start by considering an EKS cluster with a CIDR range and create a VPC. When you create a VPC, you must specify a range of IP addresses for the VPC in the form of a classless inter-domain routing, which is called as CIDR, CIDR block. So let's take an example where we are going to create an VPC. Okay, so let's say that we are creating a VPC, and the CIDR range for that VPC is 192.168.0.0/16. Okay, so this is going to provide us 65,534 IP addresses to be used. Okay, after creating a VPC, you can add one or more subnets in each availability zone. When you create a subnet, you specify the CIDR block for the subnet, which is a subset of VPC CIDR block. So let's say that we are going to create 4 subnets, okay, out of which 2 are going to be public and 2 private. So let's just consider their CIDR range. So let's say that 192.168.0.0/20, okay, which is going to provide us 4094 IP addresses. And the another one we are going to create called as 192.168.16.0/20. Okay, this will also going to provide us 4094 IP addresses. Okay, now to create private subnets, we are going to use smaller CIDR, which will provide lesser IP addresses for this demo or to understand this problem. So we are going to create 32.0/24. Okay, this is going to provide 254 IP addresses only. Okay, and the other one 192.168.33.0/24. This again going to provide addresses. Okay, so we have 2 private, 2 public subnets. Okay, so if we see, we have created a VPC, created subnets like we talked about, out of which these 2 are public and these 2 are private. And we have also created our EKS cluster okay, where we specify to use these private subnets. Okay, let's say subnet 1 and subnet 2. We suggested to use these two subnets for our EKS cluster to use. Okay, so this EKS is going to have EKS nodes. Okay, these nodes are going to be on EC2 instances. Okay, there can be multiple nodes which are there, can be present. Okay, that can be specified from the auto scaling group which is present, or the node group we call. Okay, now to understand this problem we have to understand how this EC2 present, how EC2 networking works, and how this VPC works around it. Okay, to understand this problem, okay, let's just say that we have an EKS cluster which has created EC2 instance. Okay, we have created an EC2 instance. So we know that AWS CNI plugin is used for pod networking in Kubernetes, and which uses ENI, which is called as Elastic Network Interface. ENI, okay, which is called as Elastic Network Interface. An Elastic Network Interface is a virtual network interface that you can attach to an instance. Okay, that you can attach to an instance. Okay, in a VPC, when the ENI is attached to an instance, the corresponding interface is created. Okay, so let's say that when you create an ENI, you have to specify the subnet. Okay, so let's say that we have specified the subnet where we created the EC2 instance. Let's say that private subnet we provided, private subnet 2, which has, let's say, 254 IP addresses. We know that. Okay, and the number of ENIs that we can attach is specified by the type of EC2 instance. So we know that AWS supports multiple types of EC2 instances like T2, micro, or T3, large. There are many. Okay, so depending upon those type of EC2 instances, there is a limit, like how many number of ENIs that you can attach. Okay, now ENI plays a very important role when we have to understand this IP exhaustion problem, and it will also help us to understand how the AWS CNI plugin works. So depending upon the EC2 instance type, there is a limit that is defined by AWS on how many number of ENIs that can be attached. Okay, let's talk about how this ENI works. Okay, so ENI basically is like you can attach n number of, let's say, m number of IP addresses to it, and there is like called as primary IP address and secondary IP address. Okay, the primary IP address is basically used by the host for communication with outside world, and the secondary IP addresses where you can attach multiple IP addresses. This is being used by the CNI plugin, and we'll see how. Okay, whenever you create a node, EC2 node, which is attached to your EKS cluster, okay, the CNI plugin comes in and creates an ENI for us. Okay, Elastic Network Interface, and it is going to attach few IP addresses. Okay, one is primary. Okay, where it is going to get the IP address x dot x dot x dot x, and it is going to also get secondary addresses. Okay, it is in the range, let's say that it allocates 10 IP addresses. Okay, so these 10 IPs are going to be taken from your subnet which is configured. Okay, since we have used private subnet, so the IP allocation is done from this private subnet itself. Okay, so let's say that it uses 10 of the IP addresses and one primary IP. Okay, there is another concept, or I would say there is one more component in the CNI plugin which is called as IPAM. Okay, and it plays major role over here. So we know that when a worker node first joins the cluster, there is going to only have one ENI, okay, along with all of its addresses in the ENI without any configuration. So now what IPAM does is it always tries to keep one extra ENI and allocates secondary IP addresses from the available subnet. So what happens, even though you have an ENI, the IPAM creates another ENI, okay, and allocates addresses, let's say secondary addresses. And it is also going to allocate 10 IPs over here. And from where these 10 IPs are going to come? It is going to be coming from the same private subnet. Okay. So what happens when the number of pods running on the node exceeds the number of addresses on a single ENI? The CNI backend starts allocating a new ENI until it reaches the instance type limit. So let's say that your EKS cluster over here is working and it has this ENI attached. It created some pods and started allocating the IP address from here. Once this IP address is finished, okay, it starts using from this IP range. In the meantime, what IPAM does is it is going to create another ENI for us, which is called as warm-up ENI. And this is very important. So until and unless it is going to reach the limit, okay, so we know that the type of EC2 instance we are using, it has limit to add ENIs. Okay, until it reaches the limit, it is going to add it. And this is called as warm-up ENI. Okay, this concept is actually called as warm-up. Okay, so this is important. Even though you have one ENI, okay, the CNI plugin is going to add one more ENI, okay, and that is called as warm-up ENI until it reaches the limit, and it starts allocating the IP addresses. Even though there is no worker node, or I would say no pod which is using it, but still it creates it. Okay, so that majorly eats up all the IPs that we have. Okay, so to understand this, we knew that we had 254 IPs, okay, out of which 5 are being reserved, okay. So we get 249 around, let's say, IP addresses, and then let's say that we have created an EC2 instance for my EKS cluster, okay. So this is EKS cluster that I have, and I have attached here EC2, and let's say that this is T2 micro, okay, where we can attach 3 ENI, let's say that ENI1, then again ENI2, 2, and then again ENI3. Okay, now let's say that the secondary IP address, let's say 10 IP addresses are gone, 10 are gone, and 10 are gone, and then at the time I have also created another EC2 instance. Okay, let's say that my node has 3 EC2 instances, and let's say they are all of like T2 micro. Now here if you see that 30 IPs are gone, let's say here also 30 IPs are gone, and here also 30 IPs are gone. And this way, if you start reducing it, like the IP addresses, you will go out of IP addresses, available IP addresses for your subnet, and that problem is actually the IP exhaustion problem. Hope you guys have understood the complete scenario, what happens and why this EKS IP exhaustion problem comes.
To solve this problem, we need to have custom networking. Custom networking addresses the IP exhaustion issue by assigning the node and pod IPs from the secondary VPC address spaces. To configure the same, we need to follow few steps. Okay, so let's start how we are going to solve this problem. First of all, in the VPC, you have to add or associate a secondary CIDR range from here. Okay, once the CIDR range is allocated, okay, you can check the CIDR. Okay, so currently here only one CIDR is present. There will be 2 CIDRs. Once the CIDRs are created, you have to create 2 subnets. Those subnets should be in the private subnet itself, like we have configured. Okay, so once the 2 new subnets are created, you have to associate it with the route table over here, okay, which is connected to your NAT gateway. Okay, so once this is done, you are done from the AWS console side. Post that, you have to do few settings in your Kubernetes cluster. The next step you have to perform in your Kubernetes cluster, where you have to configure the daemon set to use an environment variable called as custom network configuration as true. Once you apply this configuration, your daemon set is going to restart all the pods to apply the latest setting. Once this is done, you have to add CNI configurations. The CNI configurations looks like this. Here you have to specify the AZ availability zone, your cluster security group, and the subnet where you are applying. Note, this subnet is going to be the new subnet that you have created with the secondary CIDR range. Once this app, once this setting is applied, you also need to apply one more variable called as topology.kubernetes.io/zone. Okay, this is another variable that you need to apply using this variable ENI config label def. Okay, once this is done, you just have to restart your nodes in your node group, and once restarted, you can see that the secondary IP ranges are start getting allocation from the new subnets that you have created. Let's see a demo of implementing the same. Okay, to do so, we have created an EKS cluster. Okay, and for within that EKS cluster, we are going to do some modifications, or I would say we are going to add custom networking into it. To add the custom networking, first of all, we should able to know the VPC ID for our EKS cluster that I have exported to one of the variable called as VPC ID. Okay, post this, what we are going to do is we are going to attach a secondary CIDR range for our VPC. So to do that, EC2 and then we have to give the VPC ID which we have already got. Okay, and then the CIDR block. Okay, and for this we are going to give 100.64.0.0/16. There are two CIDR ranges which are provided by AWS which can be used, so we are using one of them. And this is associating. Okay, so once that is done, we also need to create two new subnets under the same VPC. Okay, for the same AWS EC2, oh sorry, create subnet CIDR block for the subnet is 100.64.0.0/17. VPC ID is our VPC underscore ID, and availability zone, we are using availability zone as US East 1B, and within that we also need the subnet IDs. Sorry, subnet ID, and output we need text. Okay, so ID, and we got the subnet address as this one. Okay, so we got, and we are going to add subnet underscore 1 equals this. Okay, and we are going to run the same command again, this time US1A, in which availability zone we wanted to run, and the CIDR range for this is going to be 128.0/17. Okay, okay, we got the next subnet as well, and we are going to export this into a variable called as subnet2. Now, since we have created these two subnets, we also need to attach this to the route table. Okay, so to get the route table, we have to go to AWS console. Here, if you see that you have attached two CIDR ranges for this VPC. Okay, and sorry, the flow logs, oops, sorry, the resource map, in the resource map we will able to see this. Okay, we have a NAT, and this is the route table where we wanted to associate it. So what we want is the route table. We added this, and now we are going to add AWS EC2 associate route table, and the route table ID is this route table, and the subnet ID. Right, sorry, ID subnet underscore subnet one that we wanted to give. So we have associated. Now we are going to associate the same thing. Okay, AWS EC2 associate route table. The route table is going to be same. The subnet ID is going to be subnet 2. Okay, so the association is done. And to check the same, if we go back to the VPC resource map, we should be able to see this. Okay, go to resource map, and now what we have to select is over here. If you see that both the subnets are onto a route table this. Okay, and if we want to check for the CIDRs, we can do that over here. Okay, we'll just refresh this page so that our new CIDRs will come up. And now if you see that we have 32,000 IP addresses which are available to get allocated to any of the workloads or pods which we are going to attach. So now we have created or configured from the networking side. Now we have to go and configure our CNI plugin to use this configuration. So we have done the settings which is required for us in the AWS console. Okay, so we have added a new CIDR. Okay, after that we have created 2 subnets and also attached those subnets to the route table. Now there are few prerequisites that we need to get. Okay, so we'll be getting the availability zones of our subnets. Okay, so for that EZ_1, okay, that we are going to do, and we are going to write a command called as AWS EC2 describe subnets subnet ID is 1. Okay, and what we are going to query is subnets dot availability zones. Zone and output as text. Okay, and we'll just do AZ1. Okay, we got the same. Now we have to run the same command for subnet 2, and we get it into another variable called as EZ2. And we got that. Okay, now as we spoke, this is one of the prerequisite for the next step. So we know that now we have created the configuration and we have to apply that configuration in our Kubernetes cluster, or I would say CNI plugin, to use it. So we have to first check for the ENI configurations are enabled or not. To do that, you can get Kubernetes custom resource definitions, and you should be able to see ENI configs as a custom resource definition. So here, if you see ENI configs.crd is present, which allows us to create custom ENI configurations that we can provide to our plugin, and that can be used by the CNI plugin. We also need security group of the EKS node role, okay, that we have got from the AWS console, and we are exporting it. Okay. Once done, we have to create ENI configurations. So to do that, I have a script. Okay, so here if you see or if you read, it has a API version of crd .kts.amazon, and it has kind of ENI configs. This is created with the az1 name, okay, the variable for which we have already got the value, the subnet where the subnet will get replaced, and the security group which we have just got it. Okay, once done, we just have to apply this. So kubectl apply -f pod network config 1, and then again network config 2.yaml. Once applied, you can get the CRDs. Okay, get fix, and you should be able to see the ENI configs that we have created, US East 1A and US East 1B. Since we have created the ENI configurations, now it is time for the CNI plugin to tell about using the custom networking. To do so, we have to set an environment variable named as AWS VPC K8s CNI custom network configuration as true. Once we apply this, the daemon set will restart itself. Okay, so let's just apply this configuration. Okay, now you can check that. You will see that it is terminated, and now it will create one more. Okay, now if we have seen that it is restarted. Now let's go for the next step. Now the next step for us is to check for an annotation. Okay, so here in the daemon set we have to check for the ENI config annotation is defined or not, and let's check whether it is defined or not. I guess it is not defined. In this case we have to define the annotation so that our new network configurations get applied. To do so, we are going to use our previous command where we are going to set the environment configuration, and we'll just change the variable over here. Okay, so the new variable for us is ENI config label def. Okay, and that is going to be zone. Okay, once we enable it, it is going to again restart the AWS node pod. Okay, like you are seeing. Okay, we'll just wait for it to be in the ready state. Now it is in ready state. We'll stop over here, and now we'll go for the next step. Since we are done with all the settings which are required from the Kubernetes side, now we just have to restart all our nodes which are present. So we have terminated the instance, and now our auto scaling group will create one more instance for us. Now our auto scaling group has created new resource over here, and we can see it is in healthy and in service. So if we go and take a look at the new instance, here you can see that the private IP address allocation has started from the IP range, or I would say the new subnet that we have created. Okay, and if we also take a look at the networking side, okay, here if you see the secondary IP addresses, we have seen that it stopped using the primary subnets and started using from the secondary subnet or custom networking over here. So here if you see that it is started using from the range of 100.64.194.150 instead of 192.168. And here if you see an extra ENI also has been there as per the CNI plugin. A warm-up ENI is also present. So let's just take a look by creating one resource, kubectl create deploy nginx, where we are going to use nginx image, 2 replicas in the default namespace, and it has created. Now let's kubectl get -o wide. Okay, let's just wait. And now if you see, the IP address allocation started with 100.64 instead of 192.168, which was our primary CIDR for the VPC.